Polynomial comes from the root word poly, which means many, and nomial, which means terms. So essentially, a polynomial is just an expression with many terms that consists of variables, coefficients, and involves the operations of addition, subtraction, multiplication, and non-negative integer exponents. Polynomials consist of integers, variables, and exponents, which are all called terms. Polynomials are named for their degrees. A first-degree polynomial would be called linear, a second-degree quadratic, and a third cubic, and so on. When polynomials are written in standard form, they are written in order of decreasing degree. There's also a factored form which will help you find the zeros when graphing. Multiplicity is how many times the zero of a specific factor occurs when the polynomial is graphed. In this example, we can see how the graph of an equation will change when the multiplicity is altered. Here, whenever we have x minus 2 squared, we see the end behavior is the same. X minus 2 cubed, the end behavior is different because the exponent is odd. And whenever we raise x minus 2 to the fourth power, it goes back to even end behavior. This is all due to the fact that whenever your exponent is even, your end behavior is going to be the same, and whenever your exponent is odd, your end behavior is going to be opposite. Determining the roots of polynomials, or just solving algebraic equation, is one of the oldest problems we have in the field of mathematics. But before we had this elegant way of writing out polynomial expressions, ancient people used word notation to describe these same kinds of polynomial expressions. For example, an algebra problem from the Chinese arithmetic in 9 sections circa 200 BCE says 3 sheaves of good crop, 2 sheaves of mediocre crop, and 1 sheaf of bad crop are sold for $29. Today we will write that as 3x plus 2y plus z equals 29. So here we can see how polynomial expressions has been used for a very, very long time. The first step in graphing the equation is solving the equation to find its roots. Here you set both equations equal to 0 and solve using the zero product property. So the first x will be 2/3 and the second x will be -2. Next, in finding the y-intercept of the equation, you substitute all of the x's in the equations for zeros and solve as needed, and then you'll find your y-intercept, which in this example is -8. Next, you have to rewrite the equation in standard form. First, you have to FOIL the x plus 2 squared, so that would be x squared plus 4x plus 4, and then you leave your 3x minus 2 because it doesn't have any exponents attached to it. Now you have to multiply these two, and you'll get 3x cubed plus 12x squared plus 12x minus 2x squared minus 8x minus 8. You combine like terms and you'll get 3x cubed plus 10x squared plus 4x minus 8. The leading term of the polynomial is 3x cubed, and so the end behavior of the function will have the same as the end behavior of 3x cubed. Since the degree is odd and the leading coefficient is positive, the end behavior will be as x approaches infinity, f of x will approach infinity. As x approaches negative infinity, f of x will approach negative infinity. And to put that all together on the graph, we know that our end behavior will be the same as the function 3x cubed, so since the degree is odd and the leading coefficient is positive, we'll have the end behavior as previously mentioned. So we know our two roots, which are at -2, 0, and at 2/3, 0, and we know our y-intercept is 0, -8. So we can just connect all of our points, keeping our end behavior in mind, and we will have successfully graphed our polynomial. While sketches of graphs are really great for determining roughly how the graph will look, it is important to put in a graphing calculator. Here we can clearly see that our graph does in fact have a multiplicity of 2, which we did notice from our x plus 2 squared term. We can also see more clearly the y-intercept and both of the x's. Polynomial expressions are used so often in daily life that people may not even recognize it. Have you ever been at the grocery store and you're wondering how much your total is going to be, and you kind of add up all of the items you have in your cart? So you have 3 cartons of eggs, 5 boxes of cereal, and 3 bags of chips. You can simply make a polynomial expression plugging in the values of those items and find out what the total cost is going to be. In daily life, polynomials are used by professionals. Some professions that would implement the use of polynomial equations would be in predicting traffic patterns, so appropriate traffic control measures such as traffic lights could be implemented. Economists would use polynomials to model economic growth patterns. Medical researchers would use them to describe the behavior of bacterial colonies, while engineers would use them more frequently. A civil engineer would use polynomials to design roads, buildings, and other structures, while an engineer designing a roller coaster would use polynomials to model the curves. The things we'll need to know in order to graph the slopes of a roller coaster will be the x's, the y-intercept, and the end behavior of our graph. In this example, we're asked to create the graph of a roller coaster with the following criteria. 4 minutes long, has roots of 2 and 4. Its leading coefficient is 2x, and the root 4 has a multiplicity of 2. Creating a graph from this criteria may seem kind of difficult, but in reality it's not. The first piece of criteria, 4 minutes long, is just basically another way of telling us it's going to have a root at 4. We also know that because it tells us it's having roots at 2 and 4. In factored form, this would be x minus 2 equals 0 and x minus 4 equals 0. It has a leading coefficient of 2x, so we know we have to multiply the whole thing by 2x. And the root 4 has a multiplicity of 2, meaning that x minus 4 polynomial is going to have to be squared. We can put this into our graphing calculator to see how the graph of this polynomial function will look. Next, we can plug in zeros for all of our x values to find the y-intercept of our function. Here we can see that the y-intercept of our function is at 0, 0. Another way we could have found the roots of this foundation is if we were given the equation of the roller coaster in standard form. In that case, we would have to use synthetic division to find the roots of our polynomial. In this case, we were given the roots, so we could make our equation from that and then later write it in standard form, as opposed to how we have it now in factored form. Well, this is a very simple demonstration of how polynomials are used in designing the curves of roller coasters. We can clearly see that polynomials are useful in daily life. And we can see why we learn polynomials. And we can see how polynomials are applicable to real-life situations. Tenemos nuevas historias que contar.